In this lecture, we will look at radiative equilibrium when scattering is present. If you recall from early lectures, the equation for of transfer with scattering would be like this. This is the rate of change of intensity with optical depth. This is a single scattering albedo. And here, for simplicity, we have looked at only, so we are looking only at isotropic scattering for purpose of illustration, and here mu is nothing but cos theta, that is, this is the vertical coordinate and this is the direction of your radiation, this is theta, and so you are going from 1 to minus 1 here. So, this is mu equals minus 1 here and mu equals 1 here, and omega is the single scattering albedo. Now, this equation is more difficult to solve than the equation we had done when omega was 0, pure absorption case. There this term was not there, this term was not there, and we could integrate the equation quite simply and get the answer. Now, the problem gets a little more complicated because one more term with scattering which involves integral over angle. So, there are various possible approximations for angular integration. If you recall, we discussed the exponential kernel approximation in early lectures. Which essentially involved replacing the rays traveling in various angles with a single ray at a specific angle, and we saw that this approximation was quite useful. But when you get into problems with scattering, the problem gets more complicated, and so one would look for approximations which simplify the problem right in the beginning. Okay. Now, one well known approximation which is attributed to Eddington in some books, or some books to Schumann and Schuster, and this approximation involves assuming that the radiation is isotropic, but the upward and downward intensities are not equal. That is, in many radiation problems, the upward and downward intensities usually are not equal, because it depends on from which surface the radiation emerges. But within an hemisphere, you can neglect the variation of the intensity with angle. So, this is what is known as two stream approximation. And here what you are assuming is that we can assume that all the streams going upwards are independent of angle. So, you can treat them with a single angle, and all stream going downwards are isotropic in the lower hemisphere and can be treated with one angle. But the upward and downward intensities are not same. So, this is dividing the radiation problem which has multiple streams, multiple direction into two direction, up and down. Okay. Now, this is a very useful place to begin, because once you have understood the basic way of doing a 2-stream approximation, you can also then do 4-stream, 6-stream, 8-stream, 16-stream, 32-stream. You can go on extending the problem to more and more streams, but the basic principle is same as the 2-stream model. Okay. So, in the 2-stream model, what you are doing is intensity in the upward direction is a quantity called I plus, which is valid for mu from 0 to 1, essentially in this coordinate, and intensity I prime is equal to I minus, and that involves all downward going streams. So, replacing this by a single number I plus and this by a single number I minus after integration. Okay. Let us do the integration. So, we take this equation in the last section, integrate first 0 to 1 d mu in the upward direction. When you do that, you will get the following result. The first term involves integration of only I prime is independent angle in the upward quadrant according to our assumption. So, you are integrating over mu. So, this will be half first term. Then the second term, there is no angular dependence. So, it will remain same. The third term again will not change because it is independent of angle, and the last term, because it is constant with mu, will become I minus plus I plus. Okay. So, this is for the upward region. So, mu greater than 0. For mu less than 0, you have another equation which is minus half d I minus 1 d kappa is equal to, this does not change, this does not change, I am sorry, this is I plus, I am sorry, this is I minus plus omega 2 I minus plus I plus. So, the main difference that came in this integration over angle is in the first term on the left hand side, where mu d mu integrated to plus half in the upper quadrant and mu d mu integrated to minus half in the lower quadrant. So, we have two equations and there are three unknowns of the problem, I plus, I minus and I b. The three unknowns are I plus, I minus and I prime b. We have only two equations, we will have to look for third equation. Before that, let us understand the boundary condition. At kappa equals 0, the lower boundary, the upward going radiation has to be equal to radius t by pi, that we know. And in the top of the, so we have essentially a parallel plate model, 0 and kappa 0, this is 1 and this is 2. So, in the top plate, the downward radiation has to be nothing but V 2 by pi. So, we know the boundary conditions on I plus and I minus at one point, and we have now two equations, but three unknowns. We have to generate one more condition, and that we will very soon realize we need fluxes. This is the intensity we need fluxes, but before we do that, we need to define a certain quantities. First quantity we define is the mean intensity, G. G is by definition average of I prime, and in this simple Simon-Schuster or Eddington approximation, I prime has one value in the upper quadrant, upper hemisphere, another lower hemisphere. So, this will ultimately be nothing but I plus plus I minus. Now, the flux, radiative flux, which we know all along is nothing but 2 pi minus 1 to 1 I prime mu d mu. This we know from the definition of radiative flux in the very first class. Now, this also integrates separately in the upper hemisphere and the lower hemisphere, and this will give you pi into I plus plus I minus. So, I plus minus I minus. Sign plays a role here very much. So, given these two, you can rewrite I plus as G by 4 pi plus Q r by 2 pi and I minus as G by 4 pi minus Q r by 2 pi. So, what this tells us is that the upward and downward intensities are different because there is a radiative flux in the system. Radiative flux is nothing but difference between upward and downward, and they are not same because of the radiative flux. Now, the boundary condition we wrote last time can be now written in terms of these quantities. So, you will get at kappa equal to 0, G plus 2 Q r will come out as 4 B 1, and at the top surface we will have G minus 2 Q r equal to 4 B 2. Now, if you go back to the equation for I plus and I minus we wrote down, we can now rephrase them in terms of I plus and I minus. And if you do that, you get the following result. So, now we are writing everything in terms of Q's and G's. So, we will have d q r d kappa equal to 4 pi 1 minus omega I d prime minus 1 minus omega g . So, this is the first term in terms of radiative flux, and if we consider the case of radiative equilibrium, which is what we are trying to focus on. Before I do that, let me simplify a little bit so that I make a point clear here. So, you can see here 1 minus omega comes common here, okay, and you have 4 pi I prime b, or you can write 4 E b minus g. So, under radiative equilibrium, which is the focus right now, we know that flux cannot vary with space, and so G is equal to 4 E b is the solution. So, mean intensity is 4 times the emissive power black body emission at the temperature of the medium. And this is a very nice result, because if you go back and look at the relation between G and Q, we have shown G equals 4 E b. We also know that dg d kappa is equal to minus 4 Q r, and so this implies d E b d kappa is minus q. Very simple result we got, which will be the basis of our discussion now. Now, this result is now very important because under radiative equilibrium, notice that q r is a constant. If this is a constant, we can integrate this equation to write E b is equal to minus q r kappa plus a constant. So, this result relates the emissive power of the gas, so which depends on gas temperature, this quantity, to the radioactive flux, optical depth and a constant. To get this constant, you realize the fact that at kappa equals 0, E b has to be equal to whatever the gas temperature at that point. So, the result you will get is E b is equal to q r kappa plus E b 0. You could also of course recognize the fact that at kappa equals kappa to the top, E b has to be equal to whatever is the gas temperature at the top, that emissive power. You substitute all this, then you get a simple result which says that E b minus E b of 0 by E b of kappa 0 minus E b of 0 is equal to kappa by kappa 0. This is a very simple result which we could have arrived at fairly easily, which says that at kappa equals 0, the temperature of the gas is same as the temperature of the gas touching the bottom surface. Kappa equals kappa naught, the temperature of the gas is same as temperature of the gas at the top surface. But although this result is simple and elegant, it is not that useful, because we do not know this. We do not know E b 0 or E b kappa 0. And important to recognize that in radiation problems, E b 0 is not equal to sigma T 1 to the power of 4, assuming both of the black. Even if both are black, the black body emissive of the bottom surface need not be equal to the gas black body emissive, because the temperature of the gas at T equals 0, that is, temperature of the gas at T equals 0 is not equal to T 1. Similarly, temperature of the gas at the top is not equal to T 2. This is because of radiation slip. So, because of radiation slip, we a priori do not know what E b, E b 0 are. We need to find ways to calculate this quantity from our basics. And the question arises as to how we do this calculation. How do you relate the radiation temperature of the gas at the bottom with the surface temperature? So, this slip has to be done. We had done this earlier in a different context, but now we have to do it in the context of this problem. And from the boundary condition, you have to recognize the following relationship. Sigma T 1 to the power of 4 is nothing but G by 4 plus Q by 2, and sigma T 2 to the power of 4, this is on the boundary condition, sigma T 2 to the power of 4 is equal to G 0 by 4 minus Q by 2. This we know from and here just now, sorry, G of the top layer. Okay. Now, we know that G is equal to EB, that is the condition from radiative equilibrium. So, this can be written as we also know for the solution of the equation that EB of kappa 0 is equal to EB of 0 plus or minus Q into kappa 0. Okay. So, this is coming from the direct solution of the rate transfer equation. Now, if you substitute these here, so let us go to next page. So, we will say sigma T1 to the power of 4 is equal to EB of 0 plus Q by 2. This we know already. Now, the second we are going to change it to read like, we replace EB of kappa 0 with EB of 0 and Q kappa 0 minus Q by 2. Now, we want to find what Q is. So, you subtract here. So, you get sigma T1 to the power of 4 minus T to the power of 4. This cancels out. This adds to Q. So, Q kappa 0 plus Q. So, you get a very neat result that Q, all those Q are, so we get a result that QR by sigma T1 to the power of 4 minus T to the power of 4 is equal to 1 plus kappa 0. I am sorry, 1 by 1 plus kappa 0. Now, if you recall the solution of the radiative equilibrium problem we did many lectures ago with the exponential approximation. At that time we called this quantity as Q star, a non-dimensional Q. And the result, I want to recall to you what result we got there. The result we got there is not quite same as the result here, but is quite close. It is not identical, quite close. So, let us now compare the present solution and the exponential kernel solution. It said Q star here is 1 by 1 plus kappa 0. Here we got Q star is 1 by 1 plus 3/4 kappa 0. Okay. So, the slight difference in the coefficient, and if you recall our discussion of the kernel approximation, we said that this coefficient very much is sensitive to the approximation we made for E2 of x. We said depending on the choice of A and B, we can get different results. So, once you make an angular averaging and approximation, then you must realize that the answer is sensitive to the choice you make. So, this is not identical to the result we got earlier, only because then we look at the solution for temperature. Temperature is T by T to the power of 4 by here you will get, after substituting this quantity, as 1 minus q star by 2 plus k by 1 plus kappa 0. Well, on this side, if you recall, it was half plus 3/4 kappa 0 minus kappa by 1 plus 3/4 kappa 0. Now, these two may not look alike, but they are quite close in their functional forms. So that the two methods of solving the radiative equilibrium problem, one using the kernel approximation and the other using the Simon-Schuster or the Eddington approximation, give very similar results. These two will look quite alike, and this can be made to look somewhat similar to that by looking at substitute for q star. You will get half plus kappa 0 by 1 plus kappa 0 plus k by kappa 0. If you want, you can 1 plus kappa, I am sorry. So, you can slightly rearrange it to make it look very close to the other result, but by and large the results are not very different. Actually, there should be some minus sign. So, actually I can write this as half in plus kappa naught minus kappa by 1 plus kappa naught. Now, the main thing you must appreciate here is the fact that the only difference really, these two are similar. This is also same as that, and the only difference is in the coefficient. The coefficient is somewhat different because in the kernel approximation you can relate the 3/4 to the choice of A and B in the exponential kernel approximation, but the results are not really substantially different. Now, to highlight this point of view, we will adopt another method wherein we will solve the same problem by a slightly different approach, which involves making a slightly different approximation to the problem. Before we go further, notice that we started with the problem with scattering. Notice that omega plays no role here. In radiating equilibrium, the single scattering albedo plays no role. However, this kappa is now the extinction coefficient, and hence involves both absorption coefficient and the scattering coefficient. So, in the radiative equilibrium problem, single scattering albedo does not play a role, and the scattering process is incorporated in the definition of the extinction coefficient, which is the sum of absorption and scattering. But later we will see that when you deal with problems which are not in radiative equilibrium, omega will play a very specific role in the solution. So, whether omega is important or not important in the problem depends upon whether you are dealing with a pure radiative equilibrium or you are dealing with a problem wherein either conduction or convection also plays a role, then omega will play a role. Now, let us now look at another solution, so that we fully understand the nature of the solution. So, this is called the moment method. In the moment method, you look at various moments of the intensity. So, for example, general kth moment of intensity is defined as -1 to +1 I prime mu to the power k d mu. So, this is the kth moment of intensity. So, when k is 0, you have the mean intensity. When k is 1, you have the flux. When k is 2, one can show is related to radiation pressure and so on. So, the moment method is an elegant way to approach the same problem of angular variation, but now we have an approach by which you can go for higher moments to get more and more equations. So, if we take the 0th moment, which we had already done, we know that I will call this, I will follow the previous notation, call this small I. We saw that di1 dk is equal to 1 minus omega into 4 EB and I0. This you already seen. Now, the new result we are going to now derive is by taking the second moment k equals 2 and relate I2 to I1. And if you use the Simon-Schuster approximation, one can show that I2 will be nothing but I0 by 3. That is, in this equation k equals 2, you assume intensity is uniform in the upper hemisphere, uniform and a different value in the lower hemisphere, and you integrate, you will get this answer. Now, the subject is here. You have two equations in two unknowns, but our interest is in still radiative equilibrium. So, we recognize the fact that I1 is nothing but radiative flux, I0 is nothing but the mean intensity. So, we go back to our result which we got earlier, which says dQr d kappa is equal to, so this same as what you got last time, and under radiative equilibrium you say G equals 4 EB. But if you look at the second equation for G, you get a very interesting result, which says that I'm sorry, there's a mistake. I just removed this, not right. I2 is I0 by 3, and this I1 is minus QR. Okay. And so, we substitute for I2 I0 by 3 and then use G here, we get a result which says that dG d kappa is minus 3 QR. Now, I wanted to compare this with the previous approximation, which was done somewhat differently. We got dG d kappa is minus 4 QR. That is a difference in the manner in which you do the angular integration of the intensity. Here he invoked a higher order approximation, the earlier one was a lower order approximation. So, since G equals 4 EB, okay, so you can see straight away that dEb d kappa will be minus 3/4 of QR, and you can rewrite this as QR as minus 4/3 dP d kappa. Now, this is what we did earlier as the diffusion approximation. Earlier the result was obtained in the optically thick limit. In the optically thick limit, we argued that QR is minus 4/3 dB d kappa, and through that we brought in the definition of Rosalind mean absorption coefficient. But now we are getting the same result without really invoking the optical thick limit. So, how did we get that? Now, you must remember that some of the approximations we have made regarding angular variation gets better and better as you go to the thick limit. So, although we did not explicitly invoke the thick limit, in reality some of the approximations we have used here is strictly valid only with thick limit. So, we get this. Now, we can integrate the equation. We have done this many times before. So, E b will be equal to minus 3/4 Q r kappa plus a constant, and given the boundary condition that we have, which you know about, which are same as what we did just now, there is no difference, we will get the following result. Which is identical to the result from exponential kernel approximation. So, we have got the result of the temperature variation between two plates, between two black plates, by Moment method, but the result is identical to what we obtained by the kernel approximation. So, this is happening because in the angular integration, the kind of approximation made are generically similar to the approximation we made when we dealt with exponential kernel approximation. Okay. So, what it really implies is that this temperature distribution within the gas will go as A plus B kappa 0 and C plus D A plus B kappa, I am sorry. So, A plus B kappa by C plus D kappa 0. So, A, B, C, D really depend upon the details of the approximations you have made about the angular dependence of intensity. So, for many applications those details do not matter, whether 3/4 or 1 really should not matter that much, but we do recall that this particular solution which you obtained through kernel approximation agreed very closely with the exact numerical solution. So, choice of certain approximation leads to a more accurate final result. So, what we have shown so far is the fact that the radiative equilibrium solution can be obtained in many ways, either kernel approximation or Simons-Schuster or Eddington approximation or the method of moments. All the three are really, what they are doing is really giving you various ways to approximate the angular dependence of intensity, and these approximate solutions are useful if you know what kind of angular effects are important. And as you saw when you compare this result with exact numerical solution, this can be within few percent of the numerical solution. Therefore, such approximations are very useful in the applications that we encounter in real applications. Is these approximations are extremely useful. Now, the extension of this to the situation where there is heat transfer by conduction. Now, if you recall that the pure radiative equilibrium problem had a slip at the boundary, which is quite common result we encounter in radiation transfer. Radiation transfer, the basic equation is integral equation, and hence we cannot impose the condition that the temperature of the gas at the wall is same as wall temperature. So, we must allow for the fact that there may be some slip, and this is an inevitable consequence of a problem in which we have neglected all processes except radiation. When you do that, the problem does not allow you to assume that the temperature of the gas at the wall is the wall temperature. One way to get around this is to incorporate heat conduction. So, the heat conduction is always there. We have neglected it so far to simplify the problem, but it is always there, and the role of heat conduction, which is a diffusion phenomena, is actually smoothen the temperature profile. So, we expect that the solution we got for pure radiative equilibrium, which had a slip, now will become continuous and discontinuous, and the smoothing of the sharp gradient near the wall will be done by conduction. So, conduction heat transfer will ensure that the temperature very near the wall is smoothened by the diffusion process that is inherently there in conduction. So, to remind you, if this is the vertical coordinate z, remind you that the net divergence radiative flux has to be equal to the conduction flux. So, this requirement has to be satisfied by the invoking of energy equation, but remember that this term can be quite small compared to this term, the first term, except very close to ground, where the second derivative temperature can be quite large. But this diffusion term or conduction term is essential to avoid slip. So, now there will be no slip once you have incorporated the diffusion term. The diffusion process will ensure that you have a continuous temperature profile. Now, we want to relate the heat flux by conduction and by radiation is equal to what is coming in. So, we have a simple model of the Earth's atmosphere, neglect the absorption of solar radiation by the atmosphere. So, what is coming in is really S by 4 into 1 minus alpha, that is incoming solar radiation. After energy is lost by reflection to space, all the remaining energy we are assuming is not absorbed by the atmosphere, but by the surface. in this case we can write down the energy balance at the wall, at this wall, has been equal to energy absorbed in the entire column really minus 4 by 3 pi I 1. Okay. And of course, I 1 is same as Q r. And we can again invoke the Rayleigh equation which we used earlier and show that d I 0 d kappa is minus I 1 and d I 1 d kappa is minus 3 I 0. Now, we will have additional term here coming in, which invokes the flux at the flux that is going through the system. And so, d I 1 d kappa will be related to the outgoing, this we have already invoked earlier, and the only thing now you have to do is rewrite in terms of the radiative flux, which is, if you recall, in this case I 1 is nothing but Q r and I 0 is nothing but G that we already used. And you can actually then solve the equation. The equation really says that at the top of the atmosphere, the total radiation absorbed is whatever is incoming radiation minus reflected radiation, and the intensity at the top of the atmosphere which is what is measured by satellites, both this one and this one, top of the atmosphere has to be equal to the absorbed solar radiation. So, with the inclusion of conduction, the problem does get a little complicated because of the fact that the atmosphere is infinitely thick. So, to simplify this problem, we look at a somewhat simpler exercise, wherein we assume that the atmosphere is strongly absorbing over a layer Q0 Z1, and then above that layer we assume there is no absorption. So, the simple logic in this case would be that we are taking into account only infrared radiation absorption of the atmosphere in the troposphere, but are neglecting the phenomena going on in the stratosphere. So, this is essentially a simplification which will make the problem analytically attainable. So, that is the aim of this exercise, is to give you a solution which is analytically tractable And so we do that by the following approach. We are saying that the absorption coefficient of the gas A is equal to A0 for the height between 0 and certain height. That is typically where the water vapor resides in the atmosphere, and above that height we are assuming there is no absorption. So, in this simple model, what will happen is, because there is no, since there is no absorption above that layer, our optical depth kappa now will be scaled somewhat differently from what we did earlier. It will be Z1 minus Z, because when Z equals to Z1, we are counting from the top of the atmosphere. When Z equals Z1, optical depth 0, and as we go to 0, the optical depth is going up, and here there is no absorption above that. So, what you will get is that the intensity at the top of the atmosphere will become nothing but 3/4 into S by 4 into 1 minus alpha, that is the absorbed solar radiation, by pi. So, this result you are going to get, and at the top of the atmosphere we are saying that the flux at the top of the atmosphere has to be equal to S by 4 into 1 minus alpha, because if you recall that whatever radiation absorbed by that atmosphere system has to be emitted back. So, we have here S coming, S by 4 coming in, S by 4 alpha going out, and the outgoing flux has to be equal to this minus this, because otherwise there is no balance in the Earth's atmosphere. So, this once it is invoked, you will get the solution with conduction, and the conduction solution has the advantage that you would not see the discontinuous continuities that you had observed earlier in the pure radiative equilibrium solution. Now, the details of the solution are a little bit intricate. So, if you just look at the solution, you will see that the radiative equilibrium solution would have a break here, which is a slip, and once you allow for conduction, this solution will be absolutely smooth. This is pure radiative equilibrium, and once you include the conduction term, then the solution will be extremely smooth all the way to the wall. And so, this in a way mimics what happens in the Earth's atmosphere. So, although we have simulated this as a molecular conduction, in reality what is happening is due to turbulent eddies. So, you can talk about eddy conduction. So, this term that is coming in there, which normally is used to represent the molecular conduction very close to the wall, can also be approximately used as eddy conduction in the boundary layer of the Earth's atmosphere, which is typically a kilometer thick. So, there you can assume that eddies are doing the transfer, and they are doing it similar to way it is done for molecular conduction. So, we have seen that in this lecture that we can get the result we obtained earlier for exponential kernel approximation by other means, either by assuming that the intensities in the upper lower hemisphere are constant and not a function of angle, or appealing to the moment method and using higher order moments to obtain more equations to eliminate the unknowns in the problem. But whether we use the kernel approximation or we use the moment method or the approximation of two-stream approximation of Salmon and Schuster, or it is also called Eddington, the answers are all very similar. There are slight differences in the numerical value of the coefficients, but these are somewhat minor. When you plot these results, they look extremely similar. They provide the same insight that we got from the kernel approximation. But the advantage of the neural method discussed in this lecture is that they can be invoked even in more complex problem, wherein with scattering, wherein the kernel approximation is not so easy to implement. So, we talked about two-stream approximation. Now, this has been extended now to 4-stream, 6-stream, 8-stream and so on. And with the availability of powerful computers, extending this 2-stream to multiple stream is a very trivial task. It is only extending the complication. Discuss other issues of scattering in the next lecture.